Hi, I'm Prakash Gupta, and this is my Physics 2211 Lab 4 video report. Let's get into the introduction. So, the goal of this lab was to develop simulations and to analyze resultant data to find experimental values and analyze systems. And in this lab, we did that in respect to a dynamic spring system. So, beginning from some starter code, we were to model the motion of a dynamic spring as given in a video. We're to use Tracker to extract the true motion of the spring and compare the two results. The principles at play here are Newton's laws of motion, the laws of gravitation, update equations, and spring forces. Uh, the result, the same motion was created in the simulation, but due to some tracker discrepancies, the data sets don't match perfectly. Major principles. So again, we have gravity near the Earth's surface, which is given by this force. We've got the spring force, which is given by that equation. Newton's second law, F equals ma, and the update equations, position and velocity, which we've been using throughout. Look at the video. So from this, we can see the kind of dynamic system that is happening here. We've got a spring oscillating both in the X and the Y direction as it's suspended, a mass oscillating as it's suspended from a spring hanging above. So we analyze this motion with Tracker to extract that data. And you can see as well here the sinusoidal motion in the X and Y direction depicted on the graphs. Our next step was to model this motion in GlowScript, and we used the tracker data to determine our initial conditions and some analysis of the video that was given in the original video's context to find the mass of the ball, the spring constant, and the relaxed length of the spring. We then also calculated some various constants and direction vectors that are relevant. Then in our calculation loop, we looked at getting initial values for all of our energies. And then we go through our standard calculation of different forces, summing them, and using the update equations to model their impact on the motion. And then we get our final spring forces and things, and we calculate the change in energy using the initial values we stored before and the new ones that we've just calculated. Let's see a video of what our predicted motion looks like. So we can see there were a handful of pretty big differences between the red, which is our tracker data, and the blue, which is our model. And we can dive into that a little bit more in data analysis. So we can see here our Y position and X position versus time and our change in energy graphs for our, so let's first take a look at the discrepancy here with our X position and Y position against time between our two model and experiment. We can see that the period is off, and the only real explanation that we have for that is based on that discrepancies with tracker data and sensitivity to initial conditions of dynamic systems. Here in energy, we can see that there's a lot of inverse relationships happening, and that it's generating this kind of even oscillation about zero energy. So regarding some conclusions and consistency, we were able to accurately model the motion of the mass spring system, and we were able to analyze the video using trackers. So we have done what we aimed to do. Unfortunately, some discrepancies in that data depiction and in processing resulted in those graphs not aligning very well. And that error, again, may have arisen through the sensitive nature of mass spring systems and through trackers' finickiness. Regarding some questions, what does it mean? So is the energy principle satisfied? So yes, we can see from the energy graph that the changes in kinetic and potential energy are inversely proportional, which is to say that energy is conserved, which is to say the energy principle is satisfied. And then make two separate estimates of oscillation periods. So first by examining the period of oscillation in X and Y position data. We can actually do this very easily by examining the graphs generated previously on that real versus model X and Y versus time graph that we looked at earlier. And as I pointed out before, we can measure distance peak to peak, and we can see that these are both about 1 second, which is consistent with what we want because the spring constant, which the period depends on, is the same in both directions. Thank you.